Hello students, welcome back. Let us resume our discussion in section 4. Previously, we proved the multiplicative property of Euler torsion function using the first proof, which is based upon the Chinese remainder theorem, and, well, these lemma, especially the third one. Well, let's highlight it in blue. Now, let's prove the same thing using an alternative method. I just named it as rectangular array method, but this is the method our textbook author uses, but I found it a little bit hard to follow. I don't know how to explain this well, but I'll try. I'll do my best. Let us arrange the integers from 1 to mn in a rectangular array like this. 1, 2, 3, 4, 5, 6 up to n, and then n plus 1, n plus 2, n plus 3 up to 2n, and then 2n plus 1, 2n plus 3, 2n plus 3 up to 3n, and so on. So we have m rows and n columns. Does it make sense? So far, so good. Now, let's make this observation. Each column consists of the integers of, like this, j plus n, j plus 2n, j plus 3n, and so on and so forth. So some integer n plus j, so congruent to j mod n. If you look at rows, some of them are congruent to mod whatever, that's unclear. But if you look at columns, then it's really clear. They're all congruent to j mod n. All right, now what we want is select j's that are relatively prime to n. So instead of considering this entire array of m rows and n columns, I'll select some columns and discard some columns. If I name k as qn plus j, arbitrary element here, actually before that, before removing those columns, excuse me, I need one more step. Sorry about that. I was a bit premature. I was a bit too anxious to go to the next step. Let k be an arbitrary element from 1 to mn. So k is associated to some integer not exceeding mn. So 1 through mn. So it should be qn plus j form. And if you apply Euclidean algorithm here, you'll see that the GCD of k and n is equal to GCD of j and n. Do you see that? K and n versus j and n. That's Euclidean algorithm. And then what you're going to do is select some columns and throw away the rest. Select the columns, j's, that are relatively prime to n. That is, select columns where j and n are j and n is 1. We're going to select only columns with these. And that's the same as selecting k values, arbitrary numbers here, that are relatively prime to n. Now, please remember, GCD of kmn is 1, means GCD of km is 1 and GCD of kn is 1, so we have to consider this and that. But this one, we can consider it right away by just taking some columns and then throwing away some other columns. You see? GCD of kn is same as GCD of jn. And if this is 1, then yeah, that's 1. So if you want this red, select those GCD jn is 1. This way we are going to get not the entire array, but a reduced array. We have not all those 1, 2, 3, 4 up to n. We are going to get j1, j2, j3 up to j of phi n that are relatively prime to n, because we already removed all those j's that are not relatively prime to n, and consequently by this argument removed all numbers k that are relatively prime to that are not relatively prime to n, excuse me. So over here, by taking the first entries j1, j2, j3 to j of phi n relatively prime to n, we ended up getting all these numbers are relatively prime to n, and we discarded all the numbers that are not relatively prime to n. So this red one is completely done. Red is all done. The next step is to get this thing done, which I just used purple, but we didn't start yet. But red is done. Okay. All right, following that, frankly, I found it really hard to follow. So let's take a little bit recap. So arrange like this, and each column is congruent to j, as you can say, j plus qn form, and arbitrary k, that is all the numbers here, any number here, can be written as some qn plus j form. So gcd of kn is same as gcd of jn through Euclidean algorithm. So if I select gcd of jn equal to 1, in other words, appropriate columns based on the first two entries, j1, j2, j3 up to j phi of n, then I'm going to select all the k values that are relative prime to n and discarded all the k values that are not relative prime to n, and comes down to this reduced array with m rows and phi of n columns. All right, now let's look at each column. Each column has m rows and it has increment of n. J, n plus j, 2n plus j, 3n plus j, and so on. Okay? And what we claim is these are all incongruent from each other modulo m. Really? And that has a lot to do with m and n of relative prime. So what if these two are relative prime? R1 n plus j is congruent to R2 n plus j modulo m. That means, well, j and j cancel each other out. And then m divides the difference, R1 minus R2n. And m and n are relative prime. So by Euclid lemma, m divides only R1 minus R2. And R1 minus R2 must be 0 because you see they're not just congruent to 0, but must be 0 because we have all those numbers up to 0 to n minus 1n only. You see, 0n, 1n, 2n, rn up to n minus 1n. So r and r2 are the same. So all these are incongruent modulo m. So there are m numbers that are mutually incongruent to m. As we proved, these are mutually incongruent to m. So each of them must be congruent to only one of 0, 1, 2, 3 up to n minus 1. Because there is no other integer incongruent to any of the 0 to n minus 1. We covered everything. So j may be congruent to, say, 2, n plus j may be congruent to 17, and 2n plus j may be congruent to something else, and so on and so forth. You have to have one-to-one correspondence. So we can rearrange this into this. Sm plus Sm plus 1, Sm plus 2, they're all congruent. They're all incongruent mod M. And this arrangement applies to each column. Therefore, we get phi of nj qualifying columns, and we discarded the rest. And among those, phi of n entries qualifying each term, plus 0, plus 1, plus 2, up to m minus 1. Among those, how many are relative prime to m? Yeah, these are all zeros. These are all congruent to zeros, mod m. So we have 0, 1, 2, 3, 4, m minus 1. Among those, phi of m are relative prime to m. So phi of n columns, and each phi of m entries, we have to have multiplication. That concludes the proof of this multiplicative property. So kind of arrangement argument. And if you followed, great. I really found it hard to follow. That's why I did proof 1 first. I did my best. Okay, so much for the proof of the multiplicative property. Either one way or the other, we got it done. So we are not going to come back and redo any of those multiplicative property. From this point on, we'll just use it.